Hello and welcome to Chapter 1.2 from Stevens's Matrices, Vectors, and 3D Math. In this, we are going to discuss matrices and vectors and some of the operations we can do with these things. Okay, so let me get into full screen mode here. There we go. I'll scroll up. Okay, so let's get started. We define a matrix, an m by n matrix, right? And it's a rectangular array of numbers. And this first number, m, I know that's a letter, is the number of rows, and n is the number of columns. So it has m rows, n columns, and we call it an m by n. That's what this is. It's a multiplication sign, or x. It's m by n. And oftentimes we will index a matrix denoted with a capital A with small a's, capital B, small b's. And the indexing works like this. The first number is the row, the second number is the column. For example, this A23, that's the element in matrix A in the second row and the third column. All right? And A13 is the first row, third column. Okay, the dimension is denoted m by n. We talk about the dimension of an array or of a matrix. It's the rows by the columns. And two matrices are equivalent if they have the same dimension. They have to be the same size, and every term is the same. Right? One is just a photocopy of the other. A zero matrix is denoted with this bold-faced 0, and it represents a matrix of the appropriate size that contains all zeros, as you might expect. An identity matrix is a square matrix, and it has 1s along the diagonal and zeros everywhere else. So I2 is the 2×2 identity matrix, I3 is the 3×3, and likewise for I4. And you'll see why it's called the identity matrix very soon. The transpose of a matrix A, and it's denoted term by term this way, but really what you have to keep in mind, what you got to think about, is that you're going to switch rows and columns. For example, if this is A, then the first row is 1, 2, 3. That means the first column of A transpose is 1, 2, 3. The second row becomes the second column, and the third row becomes the third column. Right, so you're just switching rows and columns. If if a matrix works out such that the transpose is equal to the original matrix, we call that type of matrix symmetric. All right. For example, if you have 1, 3, 5, and you have 2, 4, 6, and then 2, 4, 6, this matrix is symmetric, right? Because each row, and you can sort of tell by looking at it. It's sort of what you do is you get sort of a mirror reflection across the main diagonal there. Okay, diagonal and triangular matrices. A diagonal matrix has numbers. It might not even be numbers that are non-zero, but the important thing is that everything off of the diagonal is 0. It basically means that all these things, there and there, are 0. And it's called diagonal because usually these terms on the diagonal aren't 0, and so the only non-zeros are on the diagonal. Upper triangular means that the lower portion below the diagonal is 0. In other words, the upper triangle has non-zero terms. Lower triangular, again, has lower triangle that are non-zero or can be non-zero, but the upper portion must all be zeros. Right? Moving right along. Matrix addition and scalar multiplication. These work exactly how you probably would expect them to work. If you have a matrix A and a matrix B, you add them term by term, meaning you take 1 plus 2, that gives you the 3. Negative 1 plus 1 gives you the 0. 1 plus 0 gives you the 1. And likewise, so you just add term by term. The key thing is these matrices have to have the same dimension. If they don't have the same dimension, you can't add them. There is no addition if they are not the same dimension, if they don't have the same dimension, right? But if they do have the same dimension, it's just term by term addition. It's exactly what you would probably think. Scalar multiplication acts how you might expect it to act as well. In other words, if I have a matrix like this, and if I multiply that matrix by 3, and that's just denoted 3a, I just take every term in the matrix and multiply it by that number. So I would have 3 times 1 is 3, 3 times negative 1 is negative 3, 3 times 1 is 3. So you're multiplying term by term in there by the number 3. All right? Finally, 6 times 3 is 18. All right? Some properties of matrix addition and scalar multiplication. Addition commutes, right? A plus B equals B plus A. And that certainly stands to reason because addition itself commutes. You know, any two numbers, 1 plus 2 equals 2 plus 1, and so on. And so you can sort of see this in the addition process. If A plus B is just term by term addition, then you're going to get the same thing if you take B plus A. Right? Associative property, this is identical to the associative property of addition for real numbers. Doesn't matter how you group them. If you take A plus B and add C, it's the same as taking A and adding B plus C. The additive identity, the identity property of addition, if you take any matrix and add the 0 matrix, you get that matrix right back. That should make sense because the 0 matrix is just a bunch of zeros. And so when you add term by term, nothing happens. Again, they do have to be the appropriate size, though. The dimensions must match in order to add. Distributive property of scalar multiplication. And again, a scalar is just a number. Right? So if you have, say, suppose that my scalar here, R, is a 3. 3 times A plus B. Just as in the real numbers, that's the same thing as 3A plus 3B. Distributive property. Great property. One of the best. Okay, so moving on. A row vector is just a 1 by n, and it looks like a row. A column vector is just an m by 1, and it looks like what you would think of as a column. And you can get a column vector from a row vector. Suppose I take 1, 2, 3, the row vector, and stick T up here for transpose. That takes that row and turns it into a column. And you don't often have much use for this algebraically. Well, actually you do sometimes. But I use it in the book quite often because a column vector takes up more space. So if I'm working with a column vector and I want to write that into a paragraph, I'll actually write it as a row vector here with the T above it. Right, so it takes up a little less space. Okay, the dot product of two vectors. And this is where things don't work out how you probably would expect them. Right? If you have two vectors and you have a dot product. Now I know that looks like the same dot you used for multiplication. But if these two things are vectors, right, then the dot product is not multiplication. It is a dot product. It is a new operation. And what it means is you take the first term times the first term and add it to the second term times the second term, on and on and on until you add the product of the last term with the last term. So that's what this is here. So for example, if you have the vector 2, 3, 4 and the vector negative 1, 7, negative 3, then the dot product is 2 times negative 1 plus 3 times 7 plus 4 times negative 3. Right? There, there, there. So that gives you negative 2 plus 21 minus 12, and it gives you 7. Notice, this is very important. When you take the dot product of two vectors, you don't get a vector back. You actually get a number or a scalar. It's often called the scalar product because you take two vectors and you wind up with a scalar. But keep in mind, when you multiply two vectors by the dot product, you don't get a vector back. You get a number. Okay, so matrix multiplication, and this gets really confusing, but it's very important. Matrix multiplication is one of the most powerful property or operations in all of mathematics. And the way it works is not at all intuitive, right? And it's based on a whole bunch of dot products. So you really have to do the dot product to understand matrix multiplication. But here's how it goes. Suppose you take A times B. And notice there's no dot there. It's just AB. And I get a new matrix C. It is defined like this. The terms in C, the ijth, the I row, j column, that term comes from the ith row of A dotted with the jth column of B. Right? And what that means, so let's do an example because it's kind of messy. Suppose I have this matrix, A, and that matrix is a 2 by 3 matrix. And B is a 3 by 2 matrix. Notice these internal numbers. The number of columns in A and the number of rows in B must be the same. And you'll see why that is because, for example, this first term in AB, it is going to be the first row of A dotted with the first column of B. Therefore, I need to have the length of this vector be the same as the length of this vector. Right? And so that means the number of columns, this 3, has to equal the number of rows, that 3. So when you do this matrix multiplication, do it here. The first thing I'm going to do, I'm going to take 1 times 1 plus negative 1 times 0 plus 1 times 2. And that's going to be my first term, the term in the first row, first column. Now the next term, first row, second column, comes from taking the first row in A and dotting it with the second column in B. So it's 1 times negative 1 plus negative 1 times 1 plus 1 times 3. And that gives you first row, second column. If I want second row, second column, I have to do the second row in A. Second row, first column. Second row in A, first column of B. So that's 0 times 1 plus 1 times 0 plus 6 times 2. And that becomes second row, first column. Now if I want second row, second column, I take the second row in A and dot it with the second column in B. So that's 0 times negative 1 plus 1 times 1 plus 6 times 3. That gives me my second row, second column. And once you do all the math, you get 3, 1, 12, 9. Right? It's the process isn't very difficult, but there's a lot of multiplying and adding. And to do this in your head, you just have to take your time and do it carefully because there's an awful lot of places for errors to occur. And so, by the way, it is worth noting that when I took a 2 by 3, right, up here I have a 2 by 3, and I multiplied it by a 3 by 2. I needed these two numbers to match, and what resulted was a 2 by 2. right? So when you're doing matrix multiplication, you have to make sure that they line up. And then when you multiply them, you might very well get a matrix that is a completely different dimension than A or B, right? And so let's say, and let's suppose we switch the order. So this is very important. So this is AB, right? And I get this 2 by 2 matrix. If I do BA, and BA in this case is a 3 by 2, and then a 2 by 3, so I can multiply these together because the number of columns in B equals the number of rows in A. And so to do this, and it's not trivial in the sense that, you know, there's a lot going on, it's just a lot of addition and multiplication. So to get my first row, first column in B times A, I take the first row in B times the first column in A. So that's 1 times 1 plus negative 1 times 0. Right? And that gives me 1 plus 0, or 1. And to get the first row, second column, I do first row, second column. So that's 1 times negative 1 plus negative 1 times 1, which is negative 2. First row, third column is going to be 1 times 1 plus negative 1 times 6, which is negative 5. Right? And so on. If I want the second row, first column, I'm going to take 0 times 1 plus 1 times 0, which is 0. Second row, second column, I'm going to take 0 times negative 1 plus 1 times 1, which is just 1. Second row, third column, 0 times 1 plus 1 times 6, 6. And then you finish it off with the third row, first column. I get 2 times 1 plus 3 times 0. It's 2. Third row, second column. 2 times negative 1 plus 3 times 1 is just 1. And then finally, third row, third column is 2 times 1 plus 3 times 6, which is 20. Okay, so something worth noting here. When you took AB, that was a 2 by 2 matrix. When you took BA, when I took BA, I get a 3 by 3. So it's very important to notice that AB does not equal BA. Not only does it not equal BA, but it's not even the same dimension, right? Okay, so moving forward. Notes on the dot product. The dot product requires both vectors to be the same length, right? Because if you try to dot, say, 4, 2 with 7, negative 1, 3, you take 4 times 7 plus 2 times negative 1. You wouldn't have this, that's left hanging. It's got nobody to multiply by. So they have to be the same length. Technically speaking, the dot product doesn't really care if one is a row vector and the other is a column. The dot product just takes the first times the first plus the second times the second plus the third times the third, provided they're the same size, and adds them all together, right? They just have to have the same number of terms. The result of a dot product is a scalar, also known as a number in this particular course. Because of this, it's often called the scalar product. Properties of the dot product. It doesn't matter which order you do the dotting. X dot y equals y dot x. If you take a scalar times x and then dot it with y, that's the same thing as taking x and dotting it with the same scalar times y. All right. And the dot product, and I'm doing all of these without proof. We'll demonstrate them with a MATLAB demonstration, but the proofs are really just working all these things out and demonstrating that the left-hand side equals the right-hand side. Another property, the dot product distributes across addition, right? So x dotted with y plus z is the same thing as x dot y plus x dot z. Some notes on AB, matrix multiplication, right? And this first one is that the number of columns in A must be equal to the same as the number of rows in B. What that means, if you have A and multiply it by B, and you have M times N, N by, sorry, not times, N by P, these two numbers must be the same thing. The number of columns in A has to equal the number of rows in B. And when you multiply them together, you get AB, which is actually an M by B. Right? And that's what this is right here. Properties, we have the associative property. That's nice. It doesn't matter how you group them. Matrix multiplication distributes over addition. That's nice, from the left or from the right. If A is an n by n matrix, you can multiply it by the identity matrix, and you get that same matrix back. And that's the beautiful thing of the identity matrix. For example, let me just do one. So there's the 2 by 2 identity matrix. If you multiply that by 3, 2, 1, 7, notice what you get. You get 1 times 3 plus 0 times 1, which is 3. And then 1 times 2 plus 0 times 7 is 2. 0 times 3 plus 1 times 1 is 1. 0 times 2 plus 1 times 7 is 7. Notice you get the same matrix back. That's why that identity matrix is called the identity matrix. When you multiply by any other matrix, you get that matrix back. And that's multiplying by the identity on the left. You can also multiply by the identity on the right. All right, for a little demonstration here, 0, 1. You're going to take 3 times 1 plus 2 times 0, which is 3. 3 times 0 plus 2 times 1, which is 2. 1 times 1 plus 7 times 0 is 1. 1 times 0 plus 7 times 1 is 7. Notice, again, multiplying on the right by the identity matrix gives you your matrix back. Any matrix times the 0 matrix, as long as they're the appropriate size, results in the 0 matrix. And that should make sense because, again, you know, the 0 matrix is just a bunch of zeros. So when you start multiplying these things, 3 times 0 plus 2 times 0, you're going to get a 0. 3 times 0 plus 2 times 0, you're just going to get zeros everywhere, right? So multiplying by the 0 matrix does exactly what you would expect it to do. It gives you the 0 matrix back. It might give you a 0 matrix of a different size, but it will contain all zeros. Here's the big one that is missing. All right, what is missing from this properties of matrix multiplication? There is no commutative law. That means AB does not necessarily equal BA. You might get very lucky in some cases, specifically if one of them happens to be the identity matrix, but generally it won't happen. And even worse, AB and BA not only are not equal, but they're not even the same dimension. And then even worse than that, AB might very well be defined while BA is not. Right? So be very careful with matrix multiplication. Order matters. You don't want to just immediately assume that AB equals BA because it has in all of your previous math courses. That is no longer true. In fact, if you have something like, suppose you have A, which is a 3 by 2, and B, which is a 2 by 5, AB will be a 3 by 5. But if you try to do BA, 2 by 5, A is a 3 by 2, BA, that doesn't even exist, right? So not only are they not equal, sometimes one exists and one doesn't, all right? So keep that in mind. Order matters when it comes to matrix multiplication. And specifically, this will happen because the dot product is often considered just a type of matrix multiplication. For example, if you have x is 1, 2, and you multiply it by the column vector 3, 4, then the result is a single number. It's a scalar, right? It's 1 times 3 plus 2 times 4, which is 11. Right? So it's the first row dotted with the first column, right? It's a dot product, right? So you get 11. But if you do y times x, you get into a big problem because that's going to be 3, 4 times 1, 2. And what that gets, if this is a 2 by 1, and this is a 1 by 2, then when you take, let me do this again, 2 by 1, when you multiply these together, you wind up with a 2 by 2. So you want to be careful performing the dot product with matrix multiplication, because if you line it up right, it will probably do exactly what you want. But if you line it up wrong, not only do you not get a dot product, you not get the right answer, but you get something of completely the wrong size that will probably really mess things up, especially if you have this in code. For example, if I took y times x, right? This is matrix multiplication. First row, first column is 3. First row, second column is 6. Second row, first column is 4. Second row, second column is 8. So if you were expecting an 11, suppose in your code, and you got this instead, terrible things will happen, right? So keep that in mind if you're trying to do the dot product via matrix multiplication. Order really matters. Okay. Oh, this is very important. So suppose I have a system of equations, and we did this from the last chapter. I can actually express this entire system in terms of matrix multiplication. If you look at this system, there are, 3 equations, 4 unknowns. If I create the matrix A, which consists just of the coefficients, so that's a 1, -1, 1, 2, and then a 0, 1, 6, 2, and then a 1, and there's no x2, so that's a 0, 7, 5. So if I make this coefficient matrix right here, A, those are all the coefficients in their appropriate location. And then I let x be the vector of unknowns, x1, x2, x3, x4, and I let b, the right-hand side, be the right-hand side of all of these equations. Then this nasty set of equations can be written simply as a times x equals b. Right? And that starts looking a lot like algebra back in high school, right? It's like, wow, that looks really easy. The difficulty is hidden in the fact that A, capital A here, is actually a matrix, right? And by the way, this should make sense, because if you do this matrix multiplication, if you multiply this matrix A times this vector, which we consider another matrix, what you'll get is 1 times x, so that'll be x1, plus negative 1 times x2, so that's minus x2, plus 1 times x3, plus 2 times x4, that has to equal 1. If you do continue the matrix multiplication, second row, first column, I'm going to get 0 times x1, so that's gone, 1 times x2, plus 6 times x3, plus 2 times x4, that has to be 0. Likewise, if you do this matrix multiplication and you look for the third row, first column, I'm going to do this third row times really the only column, right? I'm going to have 1 times x1, I'm going to get x1, plus 0 times x2, so I don't worry about that, plus 7 times x3, plus 5 times x4, equals 3. So this system of equations, written with a great deal of time and effort, is actually written quite simply and efficiently in matrix form. Right? And then you go the other way around. Suppose you have a matrix equation that looks like this, where this is the coefficient matrix, these are the unknowns, and these are the right-hand sides. That's just AX equals B. It does represent a system of equations where you have 1 times x1 plus 0 times x2 plus negative 3 times x3 equals 8. So that's that first equation. And then the second equation is just 2 times x1 plus 2 times x2 plus 9 times x3 equals 7. And then the third equation, let's see, 0 times x1 plus 1 times x2 plus 5 times x3 equals negative 2. Right. So any matrix equation written like this is actually equivalent to a system of equations. A system of linear equations. So it's just nice little algebra with a linear system. It's linear algebra. That's part of where it got its name, right? That's just a nice simple algebraic equation. This happens to be a matrix, the A, which makes this a linear system. And so we're going to start playing around with MATLAB in the next video for this chapter. But the beautiful thing about MATLAB, and the beautiful thing about this AX equals B, if you can get your system of equations into this form, then you can use software or Gaussian elimination by hand to solve for my unknowns, right? And in MATLAB that's done, you can do it with the linear solve command, or you can just say x equals A backslash. That is not the division sign. A backslash B. And so all that handwork we did with Gaussian elimination, row reduction, row operations, to row echelon form, and back substitution, and so on, it can all be done simply with this command, provided you define A correctly and B correctly. Right? It's great. Great shortcut. Saves a ton of time and effort. It does fall short on determining infinitely many solutions and no solutions. So you have to be tricky. You're not completely out of the weeds as far as solving these problems by hand. Okay, so that wraps it up. The next video will entail MATLAB material. And then we'll do a third video, which is the worksheet problems. All right. Bye now.